Hi, in this video we are going to obtain some results related to the duality property of the Fourier transform. As we remember, the duality property is due to the similarity between the Fourier transform integral and the inverse Fourier transform integral. Now, if we have an arbitrary signal or function x of t with Fourier transform x of omega. Now we know that x of t can be obtained as 1 over 2 pi from minus infinity to plus infinity x of omega e to j omega t integrated with respect to omega. So this is the inverse Fourier transform expression. And similarly, x of omega can be obtained as from minus infinity to plus infinity x of t e to minus j omega t integrated with respect to t. So these expressions are quite similar to each other. Remember, this is the main idea in duality property. In the Fourier transform, we have a negative exponent, minus j omega t. In the inverse Fourier transform, we have a positive exponent, e to j omega t. And also in the inverse Fourier transform, we have the multiplier 1 over 2 pi. Otherwise, the two expressions are quite similar to each other. Okay, so let us obtain a result based on this similarity. For instance, in the first expression, if we substitute t equal to 0, x of 0 is equal to 1 over 2 pi from minus infinity to plus infinity x of omega. Now when we substitute t equal to 0 in the complex exponential, we get 1, and therefore we have the integral with respect to omega. Therefore, we have this result telling us that the integral of the Fourier transform from minus infinity to plus infinity with respect to omega divided by 2 pi gives us the value of the function or signal at t equal to 0. Now similarly, here in the other expression, which is the Fourier transform expression, if we substitute omega equal to 0, we have capital X of 0 equal to from minus infinity to plus infinity x of t. Similarly, the complex exponential will become 1 because omega is now equal to 0 integrated with respect to t. So the integral of x of t over the entire real axis, entire t domain, from minus infinity to plus infinity is equal to the value of the Fourier transform at omega equal to 0. So this is the first result we obtain by using the duality property. That means the similarity of the integral transforms of the Fourier transform and the inverse Fourier transform. Okay. Now we can obtain another result related to this duality between the Fourier transform and its the inverse Fourier transform, we can do the following. Again, we can start with the expression of the inverse Fourier transform once more. And instead of x of t, we can consider x of t minus t0. So this is equal to 1 over 2 pi from minus infinity to plus infinity x of omega e to j omega t minus t0 integrated with respect to omega. Okay, so this can be written as 1 over 2 pi from minus infinity to plus infinity x of omega. Now I can write this term as e to minus j omega t0 e to j omega t d omega. Now, using the expression for the inverse Fourier transform, we clearly see that this expression here is the Fourier transform of x of t minus t0. So the Fourier transform of x of t minus t0 is x of omega e to minus j omega t0. Now, in fact, we have seen this result before, and it is called the time shift property. Of the Fourier transform. Now, let us perform similar operations by using the Fourier transform integral. So here we have started with x of t minus t0. In other words, in the inverse Fourier transform integral, we have substituted t minus t0 instead of t and obtained this result. So in the Fourier transform expression, similarly, we can write this as, we can use now, instead of omega, omega minus omega 0 for a fixed omega 0. Similarly, in the previous derivation, t0 is constant or fixed. So this is equal to, from minus infinity to plus infinity, x of t e to minus j omega minus omega 0 t integrated with respect to t. So this can be written as, from minus infinity to plus infinity, x of t e to j omega 0 t, and then we have e to minus j omega t dt. So again, here now we have this expression, and obviously we have a Fourier transform integral, the Fourier integral. So capital X of omega minus omega 0 is the Fourier transform of x of t times e to j omega 0 t. So Fourier transform of x of t e to j omega 0 t is capital X of omega minus omega 0. So this is a new result, and it is called the frequency shift property. frequency shift property of the Fourier transform. But we see that these two results, the time shift property and frequency shift property, are dual properties. They are based on, in fact, we can obtain them by using the similarity between the Fourier transform expression and the inverse Fourier transform expression. Now, the time shift property is, remember, a time shift in time domain is interpreted as a phase shift in frequency domain. And the interpretation of the frequency shift property is, if you multiply a signal x of t by the complex exponential e to j omega 0 t, the Fourier transform of x of t, that means capital X of omega, is shifted by omega 0. That's why it's called the frequency shift property. Okay, now we have another important result, which is again based on the duality property. So now we can look at that result. Okay, now let us start with again the inverse Fourier transform expression and the Fourier transform expression. The inverse Fourier transform expression is this integral expression 1 over 2 pi from minus infinity to plus infinity x of omega e to j omega t integrated with respect to omega. And we have the Fourier transform expression, which is, x of omega equal to from minus infinity to plus infinity x of t e to minus j omega t integrated with respect to t. Now let us first look at the inverse Fourier transform expression. If we take the derivative of both sides with respect to t, the derivative of x with respect to t is equal to 1 over 2 pi from minus infinity to plus infinity x of omega j omega e to j omega t integrated with respect to omega. Because the only t on the right hand side appears in the complex exponential function e to j omega t, and its derivative is with respect to t is j omega times e to j omega t. From here we see that the Fourier transform of the derivative of x of t with respect to t is j omega times x of capital X of omega. So differentiation in time domain corresponds to a multiplication by j omega in the frequency domain, and we remember that this is called the differentiation property of the Fourier transform. Now we can obtain a dual result by using the Fourier transform expression. Now here, as we see in the inverse Fourier transform expression, we have evaluated the derivative of x of t with respect to t. Here we are going to evaluate the derivative of x of omega with respect to omega. So the derivative of x of omega with respect to omega is equal to, now on the right hand side, the only term containing omega is the complex exponential function again, e to minus j omega t. So we have x of t minus jt, now we are differentiating with respect to omega, e to minus j omega t integrated with respect to t. Now we can multiply both sides by j. Remember, j times minus j is equal to 1. So j times the derivative of capital X of omega with respect to omega is equal to, from minus infinity to plus infinity, t times x of t e to minus j omega t integrated with respect to t. So from this expression we clearly see that Fourier transform of t x of t is j times the derivative of capital X of omega with respect to omega. Now in differentiation property, differentiation in time domain corresponds to a multiplication by j omega in the frequency domain. Here we have obtained a similar result. Multiplication by t in time domain corresponds to differentiation in the frequency domain, but here we have the multiplier j as well. So this is called the differentiation in frequency domain. This property is called differentiation in frequency domain. Okay, so we have obtained, in this video, we have obtained three results by using the duality property of the Fourier transform. That is, by using the similarity between the Fourier transform and the inverse Fourier transform expressions. Thanks for watching.